I'm going to present you how machine learning can enhance user experience in virtual reality. So the first thing we may ask is, what is virtual reality? So virtual reality was a term spread by Jaron Lanier during the 80s, and it refers to something that is almost real, but still quite not real. So we have an illustration of what people might think about what is virtual reality. And actually, there are several levels of immersion that still refers to virtual reality, known as the Milgram Virtuality continuum. So on the full left, we have the real world as we live in, so without any screen, any computer-generated content. And on the full right, we have something that is close to what the movie The Matrix represents. So for those who don't know what The Matrix is, it's a virtual world so realistic that and in which people are so immersed that they are even not aware that this is not the real world. So between those two extrema, we have a different level of immersion. So we can have an example of an augmented reality scenario in which, for instance, a technician can have a look at the machine to have additional information to know how to service it. We can integrate video stream from cameras into head-mounted displays to integrate real items from the real world into the virtual environment. We can have non-immersive virtual reality to display information on the desktop screen, or we can even go further with the immersive virtual reality that is, for instance, illustrated on this picture, in which the participant is really immersed into the virtual environment. So to achieve such high level of immersion, head-mounted displays needed to be developed, and the first one was designed by Ivan Cheverland in the 1977 during his PhD in the MIT. And the device was so heavy that it needed to be mounted on the ceiling, and the information display at that time were quite basic. He already defined that the ultimate display would be a display that might be able to replicate some physical interactions. For instance, if it would display a chair, one would be able to sit on it, and if one was about to take a bullet in such a virtual environment, these people might be able to die. So of course nowadays we don't have such kind of immersion level, but still we made like quite a lot of progress. We have professional device and more consumer grades one. So for gamers, most of them already know the HTC Vive or the Oculus Quest. And nowadays devices are even standalone, which means that we don't need to buy a gaming rig to be able to play video games on those devices. So a bit of caution on the terminology. In the industry, immersion is often used to refer as the involvement of the player into the virtual environment, whereas in the academics, Mills later defined the immersion as what the technology can deliver to the user. So those are mainly technical characteristics, as we can see on the right. So it can be the field of view of the device, it can be the refresh rate, the color fidelity, all those kind of technical aspects. So yeah, the word is really to make the distinction between the immersion referring to the characteristic in the academics and on the subjective feelings which can be felt by the users. So presence is the subjective response of participants to what the immersion delivers, and it describes how the user reacts in the virtual environment. So we can see, for instance, someone walking on a small path and he extends his arm. So he has the feeling that he might be able to fall, although he's walking on a flat surface, so which gives hints about the fact that this player is experiencing presence. As presence is a subjective feeling, it means that everyone has a different level of presence to the same stimuli, so to the same immersion. And a good wording to illustrate presence is really the feeling of being there. And once more, presence should not be confounded with the involvement, for instance, into a game. An illustration of a scenario in which a user might feel presence was an experiment we performed in collaboration with VR Rescuer, so a Swiss startup, in which we asked participants to perform CPR in a virtual environment. So the idea was to have a really simple setup, only composed with 2 trackers, and ask participants to train themselves at performing CPR. Despite the simple setup involved, we still managed to reach a sufficient amount of presence, given the involvement of participants into the scene, the deformation of the virtual body of the mannequin. And we observed that even with haptic feedback, we had better performance for the training of the users. So given the previous example and also one illustration of what we can have in virtual reality, many applications still don't include the full body animation. And the fact that we have a virtual body is really important if we want to have a referential into the virtual environment. And providing simply an avatar in this virtual environment is not sufficient for one to embody it. So Kiltenial defined the sense of embodiment as a composition of 3 subcomponents, which are the sense of self-location. So I am located where the virtual body is located. This can be achieved by having the camera located at the position of the virtual head. The sense of agency, which is the fact that I control the movement of the virtual body as if I was controlling my own body. And the sense of body ownership, which means that I own the virtual body I see. So for instance, if the arm is collocated with the location of my real arm. So the question is, how do we provide users with a virtual body? So the first thing is to have an interface between the real world and the virtual world and the computer, so that the computer knows what is the current posture, for instance, of the users. This interface needs to be real-time compliant, as Farrer et al. Showed that beyond 300 milliseconds between user action and the perception of the reaction, we may have disruption of the sense of agency. And disrupting agency also disrupt the sense of embodiment. And unfortunately, most of the tracking solutions are often subject to artifacts. So here we have an example of tracking of a Mocap solution. So there are several technologies to acquire users' motion. We can have camera-based solution and camera-free solution. For the camera-free solution, we can have magnetic field sensor, which are located in the 3D space. And given the magnetic field, we can recover its position, although it is quite sensitive to metallic parts. We can have a mechanical solution. So this one, the illustration is a bit old, but the idea is, for instance, to have strips on, for instance, a glove. And when those strips get bent, the resistance of the material changes, and we can recover so the bending of the fingers. Or we can use accelerometers. So we define an initial position, and then after integrate the acceleration over time to maintain the position, but those kind of solutions are often subject to drift. On the other hand, we have camera-based solution. So we can either equip users with markers, which is the case for active and passive tracking. In the active case, we only have LEDs that are used as markers, which give additional information. And on the passive one, it's just like a reflective sphere, for instance. On the computer vision side, it's just using, for instance, an RGB camera to recover some features. So, for instance, a point in 3D space. An example of a solution that uses computer vision is the tracking from the Oculus Quest, because this device is made to be standalone, which means it doesn't have access to any external tracking. So it needs to be able to locate itself in such a way that if someone is about to turn on his head on the right, the vision also shifts to the right. And this complex schema is mainly here to illustrate the fact that machine learning is only used in a small part of the whole pipeline. So really the idea is only to use, for instance, a traditional algorithm to take care of what traditional algorithms are really designed for, and machine learning to cover, for instance, parts which are more designed for the machine learning. So the idea is really to have an integration instead of having one thing doing the whole process. More in line with what we performed within our lab, we implemented an animation pipeline for hand animation, and we used optical tracking. And one issue we have is that if both hands are overlapping, we have what we call occlusion, so the camera can no longer see the position of the trackers. And this prevents the whole animation of the hand. So to address this issue, we used an autoencoder, which is a type of neural network which aim to retain the core meaning of a data set to fill those occlusions. So the idea was to extract the fingertips position within the hand referential, and then after train the neural network so that the input matches is exactly the output, because if we don't have any occlusion, basically we expect to have as an input the output. And during the training we introduce artificial occlusion, so we cut off some of the inputs in such a way that the neural network get familiar with those kind of occlusion and get robust to this situation. And once the neural network was trained, it was integrated in the real-time pipeline to animate, to fill all the occlusion within the hand referential. So now, let's say we have all the information from the tracking solution without any occlusion, etc. How do we do to animate an avatar? So there are several ways of animating an avatar. We can either deform an existing mesh, or we can use a skeleton rig. Using a skeleton rig allows to represent the whole avatar position with a set of rotation for each joint. And this allows also to enforce some constraints, such as the bone length, for instance. In machine learning, most of the time, the features extracted are the location of, for instance, the joints, which means it's more complex to enforce bone's length. And also, if you only define a bone with 2 points, it means you can have any rotation that makes the bone still passing by those 2 points, potentially a valid solution. So if we have the position of the effector, so the targeted position, so let's say this is the position of the marker, and this is the kinematic chain that represents my arm. If I want to have the arm reaching the position of the target, we need a tool that is called an inverse kinematic, and it takes into input the kinematic chain and the targeted position, and then it's to compute all the joint rotation to satisfy the fact that the effector matches the targeted position. So there are several methods that that can be used to solve those kind of problems. We can have an analytical method which takes basically mathematical formulas, and you can invert it to retrieve the angles, but it's not always applicable, especially for full body animation. We can have a Jacobian-based method, so it's more heavy in terms of computational cost, or we can also have data-driven approaches and hybrid methods. If we go back to the animation pipeline for the hands, we use a data-based animation, where we, in addition to the position of the fingertips position, we had information from accelerometers that were used to have a ground truth for the joint rotation. And once more, we use an autoencoder to be trained with the input of the fingertip position and as an output the ground truth to recover to predict the joint rotation of each of the finger, and at the end having a realignment process to make sure that the fingertip is always aligned with the marker at the end of the fingers. So this is an example of the result we have. So we can see in green the position of the input from the Mocap. The sphere, when they turn black, means that they are occluded, so it means that it's no longer seen from the motion capture. And we can see that even if we have some occlusion, the system is more or less able to fully recover the position. So we can have hand checking, and we can also have hands like almost completely occluded. So this is one way to animate, but we don't necessarily need to have something that is really realistic. For instance, in the paper Cool Moves, the author only took the inputs from the controller and the head-mounted display. So this is really a simple setup. And they use a pre-recorded dataset of sportsmen in different type of sport to animate the full body avatar. So the idea was to construct, to extrapolate the dataset of the sportsmen, only taking into account the controller position within the head referential, with also the velocity and acceleration, to scale up and down the speed, so that if the user performs the motion more or less faster, we can still have the recognition of the poses. The dataset is then trimmed down for each frame in order to only retrieve frames that are more or less close to the current position of the user. And then the nearest pose are computed for each, based on each arm, and then after interpolated to reconstruct the position of the full body. At the end, there is also final smoothing of the animation to avoid jitter, and we can see on the pipeline that we have the initial pose taken into account, so only the position from the controllers and the head here, that leads to the final pose here. So as we can see, we have some difference in the animation of the feet, but the question is it really a huge matter or not? And some study showed that humans are quite tolerant to motion distortion. Typically, Burns and al. Studied the distortion, for instance, when a hand was about to go through a table in virtual reality. So here we have the position of the real hand and the position of the virtual hand. And the idea was that the user accepts more a hand that stays above the table than a hand that goes through the table. And the values are quite important. We can have a tolerance about like 45 degrees in the elbow joint without user noticing if this is correctly done, because we are more focusing on the visual feedbacks than on proprioception. And this is even more important if we help participant, if we use the voice distortion to help participant to achieve some goal. So as voice distortion are, the tolerance for voice distortion are different for each participant. It needs to be calibrated if you want to be able to use it without breaking the embodiment. And this is the work of one of my colleagues, so Dr. Porsu, who used a mix of E-greedy policy and upper confidence bound algorithm to detect the maximum threshold for each participant. So the idea was to have a reaching task in which participant needed to follow the targeted sphere in green. And the real position of the arm is displayed in red but not visible to the subject, and the displayed position is in solid gray. And it played with the amount of distortion that can be introduced. And the reward for the algorithm was the gain of the distortion if the distortion went unnoticed, and the opposite of the distortion if the gain was observed by the participants, which means that the goal of the algorithm was to increase as much as possible the gain without having someone noticing it. And his results show that reinforcement learning was better at providing a robust detection threshold than traditional methods such as the staircase. So in the case of my thesis, I am working on the embodiment of avatar with different shapes and proportion. And we need to use those kind of distortion to be able to embody avatars with different shapes. And the animation pipeline, although it's not machine learning, is kind of similar in the way that the computation of the virtual effector's position is a sum of weighted vectors toward the body of the real user. And this animation also needs to be within the range of the tolerated distortions. So to finish with a few insights on how machine learning can also help the user's experience in virtual reality. One of the main issues we have in virtual reality is the motion sickness, which occurs when we have a conflict between what our inner ear told us, for instance, the fact that we don't move, and what the visual clues tell us. So for instance, there is an acceleration. And we can use physiological data to try to predict if someone is about to getting sick in this virtual environment, or to try to understand what are the causes of this sickness, to allow developers to be able to build games that won't lead people to be sick. Another illustration of cases where machine learning can be used is in pose recognition. If you want to have a bidirectional interaction with in your game and to allow user to express meanings through the hand position, this can be useful also for rehabilitation. With introducing distortion to help participants to perform a task, to motivate them in such a way that they will recover in the end more motor skills than people without it. To generate virtual world for games, or also to recognize the emotion in the simulation. So I would like to thank my two thesis advisors, so Dr. Ronan Boulic and Bruno Herbelin, and you for your attention. Thank you very much.
Hello, thank you very much for this presentation. I have a question. How far are we from having real life avatars in video games? So instead of having like a virtual avatar that is not like realistic, like in a certain point of time, are we going to be able to like live it in ourselves, like with our real bodies?
So thus far we are almost able to have like animation of the hand that works perfectly fine. For instance, Oculus, Meta, now released a new version of the tracking solution for the Oculus Quest, which also allows beam manual interaction. So before we were not able to have hand overlapping. And also some startups are investigating for tracking system with cameras a bit outside of the HMD to be able to locate the position of all the limbs. But one thing that needs to be taken into account is that when you try to reach realism, you have what we call the uncanny valley, which means that the closer you reach the realism, there is just a gap before having the highest level. So people might prefer to have, let's say, a wooden avatar that will kind of smooth the imperfection of the animation than having something that looks almost as real as a real body, but with a small imperfection that will make that the avatar you see is kind of someone really creepy because the animation is not perfectly fine.
Je me posais la question, le fait qu'on puisse projeter un avatar, donc on reprend quelque chose qu'on est actuellement en train de faire dans de l'informatique, donc on numérise tout ça et on crée un avatar informatique qui peut lui aussi être reprojeté dans des machines avec les capteurs associés, les joints associés et les vérins associés, parce qu'au final, c'est un peu le contre-procédé de ce qu'on a fait avant. Donc l'acquisition, le rendu. Et est-ce qu'il y a des applications qui sont intéressantes? Je pense déjà par exemple à la médecine avec le télétravail du médecin et au-delà de ça aussi un peu alors c'est un peu fantasmé encore, hein, on est encore dans le futur parce que c'est quand même des technologies qui sont assez futuristes, mais pas tant que ça parce que comme on voit sur les vidéos, ça a pas mal déjà avancé. Est-ce que les guerres un peu robotiques, c'est une possibilité? On parle dans les 15 prochaines années. Est-ce qu'on peut maintenant, par exemple, si on se met dans un laboratoire, avoir un robot parfaitement animé avec les mouvements qu'on fait avec des capteurs? C'est-à-dire, est-ce que le télétravail robotique, c'est possible?
Alors, il me semble qu'il y a un professeur japonais qui a effectivement fait ça avec un avatar à son image, très réaliste, et qui avait carrément, il me semble, envoyé son clone donner un cours et sans que les personnes, il me semble, ne s'en rendent compte. Mais ça a vérifié, mais il me semble que ce genre de choses est donc déjà plus ou moins
déjà arrivé.
faisable.
Ok, d'accord. Bah, merci beaucoup pour votre réponse.
Je t'en prie.
J'avais deux questions. La première, vous avez dit que vous faisiez appel à l'apprentissage par renforcement. Mais avant de converger, c'est assez long. C'est-à-dire qu'il faut répéter beaucoup les tâches. Est-ce que vous pourriez nous dire si ça ne pose pas un problème d'utiliser l'apprentissage par renforcement de ce point de vue-là? Et la deuxième question, c'est très bref. Vous avez mentionné la vallée de l'Intrange, Uncanny Valley. Est-ce que vous avez testé, c'est-à-dire est-ce que vous avez montré qu'il y avait effectivement ce sentiment très désagréable lorsque l'avatar se rapproche vraiment de la réalité? Parce que c'est une hypothèse qui a été émise par un chercheur en 75, mais elle n'a jamais été vraiment totalement validée empiriquement. En tout cas, ce que je sache, mais je ne sais pas. Voilà.
Donc pour la première partie avec le reinforcement learning, il me semble que ça devait être effectué sur peut-être une centaine de trials. Donc c'était une combinaison en fait de l'UCB et de Eagle Policy. Au début, c'est essentiellement des décisions qui sont prises au hasard, et puis après ça laisse de plus en plus la place donc à l'UCB. Et le gradient, et le learning rate diminue aussi de plus en plus pour que le système se force à converger par construction. Donc ça, c'est l'approche qui a été en tout cas utilisée donc par mon collègue. Donc voilà, donc il y avait une convergence aux alentours, il me semble, d'une centaine de trials. Il faudra que je vérifie dans le papier, mais donc de toute façon, c'était assez limité par construction pour être sûr qu'on arrive à une convergence. Et pour la deuxième question, donc sur le test de l'Uncanny Valley, je ne l'ai pas testé personnellement et je n'ai pas le state of the art tout de suite sous les mains pour pouvoir vous répondre.
Hi, so my question will be in English. I just want to ask, I don't know if you presented much about your current, I think you're doing your thesis at the moment. So how is your progress with that? And, what are some of the findings that you've done so far, or how far have you reached in your research and answering your research question? And also my second part to my question is, what do you hope to see coming into the future with VR and also immersion? What do you want to see as happen in the future, or what things do you want more to be investigated?
Okay, so for the first part, well, it's kind of complicated because initially you make a plan of what you are about to do during your thesis, and it's never as you planned. So I worked on different topics. Some are a bit less in line with what I was expecting to work on, and obviously I'm a bit delayed at least. But I guess it's kind of the traditional pattern for doing a thesis. And for what I'm expecting to have in the future, so I expect to have even more powerful HMD that takes advantage, for instance, of upscaling of the picture to only focus on the rendering of some area, which is called the fovea rendering, where you use the data from the eye tracking to know where the people is looking at, and then after you compute only high resolution picture in this spot area, you have less accurate information on the edges. With the increasing technology, I mean, if we use this kind of technology, we can spare more resources to increase, for instance, the tracking. So yeah, once more, we can have a higher tracking data. So maybe one day a full body tracking without having any external devices. Hopefully, it will be like completely sensible to occlusion or all those kind of issue. Yeah, I mean, we need to wait a little bit to be able to see those kind of things. But I really hope it will happen one day, and hopefully not in decades or those kind of things.
Yeah, I just want to ask maybe one little thing, like how would phobia, like rendering, be able to help better with the full body tracking?
No, it won't help directly for full body tracking, but if you use FOVIA rendering, you will save some computational resources that can be after used for something else, or it can just be used to cut off some energy consumption to be used on another chip that is more dedicated for full body tracking. It's not like directly linked, it's just that if you spare some resources, you can reallocate those resources to something else.
So you find that's like the new, like the direction that VR development should be going is towards more focus on?
I guess they are working on many different topics at the same time. So the tracking, of course, is one field of interest, but also on the rendering process and dedicating like hardware chips to take some workload that are done by the CPU that can be shifted to some accelerated chipset.
Okay, thank you so much.
Thanks.
Good luck with your thesis.
Thanks a lot.
Donc, dans cette présentation, M. Delehaye nous a présenté différents exemples d'algorithmes en machine learning pour améliorer l'expérience utilisateur en réalité virtuelle. Alors, qu'est-ce que ça veut dire l'expérience utilisateur? On a parlé en fait de l'importance de simuler la présence ou aussi du sense of embodiment, comment incarner en fait un avatar, parce que créer un avatar n'est pas suffisant. En plus de créer un avatar, il faut pouvoir que la personne le localise, elle puisse le contrôler et elle puisse se l'approprier. Ce corps, c'est le mien. Alors, sur le point, comment créer un corps? Donc, on a vu quelques technologies en capture de mouvement, en Mocap, et le défi est bien sûr d'être en temps réel. Et un des principaux défis de la capture de mouvement, c'est l'occlusion des marqueurs. Donc, certains marqueurs vont des fois se retrouver cachés, et ça va faire apparaître certains problèmes lors de la création de cet avatar. Pour cela, on peut utiliser donc des algorithmes afin d'animer, de révéler certains éléments cachés, comme par exemple une main qui serait en dessous d'une autre. Ensuite, sur le deuxième point, comment animer un avatar. Donc, on a vu la création de squelettes et de pouvoir les animer, donc pouvoir bouger, donc avoir des angles articulaires sur le squelette. Et encore une fois, on est capable d'utiliser le machine learning pour pouvoir bouger, parce que sinon, ça demande des calculs qui sont trop longs ou trop complexes. Et donc, par exemple, il nous a présenté Cool Moves, dans lequel on va animer des avatars de corps complet avec des mouvements de sport. Et pour cela, comment on fait? On interpole certains points et ensuite, on se base sur des bases de données de mouvements au préalable enregistrées pour pouvoir animer cet avatar. Mais enfin, il a abordé un dernier point qui me semble très important, c'est est-ce que c'est absolument nécessaire d'avoir une telle précision dans l'animation du corps? Est-ce que la personne serait capable de remarquer s'il y avait quelques différences? Et en fait, on se rend compte que les êtres humains, donc nous sommes en fait très tolérants à la distorsion humaine. Donc, c'est-à-dire qu'il y a un décalage entre la position ou le mouvement d'un avatar et ce qu'on fait dans la réalité. Mais ce qu'ils se sont rendus compte aussi dans son laboratoire, c'est que ce décalage, il est différent pour chaque personne. Et donc, ça a besoin d'une calibration où on va détecter en fait le seuil pour chaque participant à partir duquel ça devient intolérant. Et donc, M. Delehaye travaille sur cette notion de distorsion de corps durant son doctorat. Et enfin, pour conclure, il nous a présenté d'autres exemples de machine learning dans lesquels le machine learning pourrait être utilisé pour améliorer l'expérience utilisateur en réalité virtuelle. Donc, il nous a proposé le motion sickness, donc le mal du mouvement qui peut apparaître en réalité virtuelle. On essaie de trouver d'où ça vient, puis comment améliorer l'expérience de l'utilisateur. On a aussi tout ce qui est reconnaissance de pose et enfin la génération de mondes virtuels. Merci pour cette présentation très intéressante, M. Delehaye.
Thanks a lot.